Good afternoon, all of you. So, today afternoon we are going to discuss about a reflection of waves. Okay, as part of the reflection, morning session I discussed about already reflection of a sinusoidal wave or simple harmonic progressive wave at a rigid end. Okay, in that case we discussed about there is a phase change 180 degree you can observe in the case of reflection in the rigid end, and crest will become trough and trough will become crest. Okay, that is in the rigid end. We'll come to reflection of a wave at a free end. You can observe here already. So the crest will reach the free end, so that again it will reflected as a crest only. So in the case of a free end, crest will form the crest and a trough will form the trough, and the phase change is 0. Phase change will be 0 degree or 0 radian. Up to this we have discussed. Okay. So based on that reflected wave, we can write. So reflection of wave, progressive wave at a free end. Are you able to see the screen? So in the case of free end, what I said. So for the free end of a rod, you can take this crest will reach this point. Again, after reflection, it will give only crest. After reflection, it will give only crest. So that crest will become crest. That we discussed already. Okay. And then trough will become trough. Trough will become trough. And phase change is 0. Phase change is 0. Okay. Now, how the reflected wave? So by incident wave is like this. Y incident is equal to AI into sine omega t minus kx. The reflected wave is YR is equal to AR into sine omega t minus k into minus x, plus phase change is 0. Okay. The reflected wave is AR into sine omega t, AR into sine omega t minus into minus plus kx. Plus kx plus 0, no change. Are you clear this? The equation for the reflected wave in the case of a free end, phase change is 0. There is no change in the wave equation. Right. This is about transverse wave. This is about transverse wave. I said there is another type of wave called longitudinal wave. Mechanical waves are two types, transverse and longitudinal. So now we can go discuss about longitudinal waves. Longitudinal, how they reflect. Okay. Longitudinal waves. Okay. So what is the longitudinal wave? What I said, have remember? While the wave is traveling in a medium, the vibration of the particles along the direction of wave propagation. Suppose wave is propagating like this, left to right. The particles of the medium also will vibrate from the left to right, again left, again right. Are you clear? Parallel to the propagation of the wave. That is longitudinal wave. Example, sound waves. Example, sound waves are the longitudinal waves. Now the sound waves, how we can take in the form of compression and rarefaction. Sound waves you can take in the form of compressions and a rarefaction. Compression and a rarefaction. The combination of compression and rarefaction will give the one longitudinal wave. Now, once it is reaching a rigid end, what happens? Okay. So actually, this means from rarer to denser medium also can say. From rarer to denser medium. The wave is propagating from rarer to denser medium is same as the wave hitting the or wave incident at a rigid end. Wave incident at a rigid end. Incident at a rigid end is same as the wave is trying to transmit from rarer to denser medium. Now in such a case, you can imagine, first you can say this is a compression. This is the compression. Where the pressure is high, density will be high, particles of the medium will be very condensed. Then the rarefaction, particles are distributed. Okay, that is rarefaction. Next, compression, like this. Now, suppose this is the rigid end, like a wall, you can imagine. This is air medium. All of a sudden, there is a wall, solid medium. So that it is a rarer medium, this is a denser medium. Now, in that case, how the compression will become? See here, compression is here hitting. Let us say compression. We can take rarefaction or compression, whatever. Suppose let us say compression. Compression is hitting at the solid surface. That is the rigid end. Are you clear this? Then these molecules already in compressed mode, then trying to hit the wall like this. Then after that, what you can expect? The molecules will reflect back. Reflect back. Are you clear this? That means compression will be reflected back as a compression. Compression reflected back as compression. Are you clear this point? This is the reflection of a longitudinal wave at the rigid end or from rarer to denser medium. Both are same. So it is reflected back, again compression will be formed. So that the compression reflected back as a compression. Are you clear this point? Then what about the phase change? What about the phase change? Here phase change is 180 degree. Phase change is 180 degree or pi radian. How it is? See here, this particle hit and reflected back. That means incident particle and reflected particle you can see. What is the phase difference between incident particle and reflected particle? 180 degree. Because this is positive x-axis, this is negative x-axis. Okay. So that, are you clear this point all of you? This is very, very important. In the case of longitudinal wave, compression will become a compression reflected back, but a phase change will be 180 degree. Okay. Next. Similarly, the rarefaction reflected back as a rarefaction, no doubt. Rarefaction reflected back as rarefaction. That means R reflected back as R. Are you clear this? So phase change is 180 degree. Now this is about rigid end. What about free end? Free end. Free end, or else you can say the molecules are going from denser to rarer. Denser to rarer. Okay. So free end case where we can see. Suppose you have a flute. You have a flute. Okay. You are doing a flute or clarinet. So you are making whistle so that compressions or rarefactions will be formed inside that. So here density of air is high inside the flute or inside a clarinet, inside a musical instrument like a pipe, open pipe. So inside air molecules is high, denser medium. While coming out, this is a rarer medium, normal air medium. So less denser compared to inside to outside is less denser. Then in this case you can observe here, this is from free end. This is a type of free end. This is a type of free end. Are you clear this point? Understood or not? When the air is blowing out from a flute or from a clarinet or whatever musical instrument, then in that case, the end point is like a free end, not rigid. Are you clear this point? Yes or no?
Yes.
Right. So in that case, inside air molecules are high denser because of closed. Outside is open, so that less denser, relatively less denser air molecules. Then denser to rarer. Then this manipulates the denser to rarer. Then in such a case, suppose a compression is reached endpoint. This let us say endpoint P. There is a compression is reached. Compression of air molecules. Compression of longitudinal wave. The compression will come out. freely. Then if it is compression come out freely, what happen? Compression will become rarefaction. Because it will come out freely now, that will become rarefaction, go away. Okay, and some molecules of rarefaction again will go back into the reflected back into the flute or pipe. Some molecules will reflected back into the pipe. So that means compression will become rarefaction and rarefaction only reflected back. So that what happened at the free end in the case of longitudinal wave, compression reflected back as a rarefaction. Are you clear this? Compression reflected back as a rarefaction. Yes or no? This is at the free end. Okay. Here what is the phase change? Phase change is 0. Phase change is 0 in the case of free end. Okay. Similarly, rarefaction reflected back as a compression. Rarefaction reflected back as a compression. Okay. So this is about reflection of longitudinal waves. Reflection of longitudinal waves. Are you clear this? All of you? Reflection of longitudinal waves? Yes. So this is about understanding about reflection of transverse wave as well as longitudinal. Slight deviation is there in the case of longitudinal waves and transverse waves. Akshay Nandani, SSSR. Okay, right. Right. So now, once you can understood reflection, then we will go for standing waves. Before going to standing waves, small terminology we need to understood still. Okay, that means the reflected wave superimpose with original wave, then it will form the standing wave. So before going to that, I will define the velocity of the longitudinal wave. Velocity already I said v is equal to omega by k. How it is came, I will tell you. Speed of a traveling wave or longitudinal or transverse. You can say velocity or speed. Speed of progressive wave, progressive or traveling wave. Progressive wave. So derivation I will tell you how it is become v is equal to omega by k. This derivation I will show you. Or v is equal to n lambda, how it is. So that is the speed of progressive wave. Here you can see, let us consider a wave propagating along x-axis. This you can take time along x-axis, y displacement of the particle. Suppose a wave pattern like this, y is equal to sin omega t, like that you can take graphically. Now after delta t instant of time, is already, let us say, propagating with v speed. You can imagine a wave is propagating with v speed. Now after delta t time, the situation will changes now. That means the position of this wave shifted from this point to next point, next position. Next position means how we can imagine like this. Next position. Okay, like this you can imagine. Next to this. Okay, the wave is continuing like this. After delta t time I am talking. So let us consider this particle and this particle. That means same particle after next position, after delta t time. Then the distance traveled is wave delta x. Delta x will be traveled horizontally in a delta t interval of time. Are you clear these points? Okay. The distance traveled by the wave along positive x-axis, delta x in a delta t interval of time. Then what you can say, speed is equal to distance traveled delta x by time taken delta t. Can I write like this? Speed v is equal to delta x by delta t. Okay. So now two different positions of the same particle. So for the same particle, in terms of particle I can say same particle, two different positions. two different positions while the wave is propagating. So in that case, normally wave equation you can write y is equal to a sine omega t minus kx is the wave equation. So in that case, while this delta t interval of time, this phase value omega t minus x, okay, this phase value you can say that is omega t minus kx, the phase value will be constant for a given particle. For a given particle, omega t minus kx is equal to constant. Is the condition. So in that case, if omega t minus kx is constant, then you can differentiate. You can write omega t minus kx or kx minus omega t, no problem. So that you can differentiate with respect to time now. This constant value, phase value, differentiate with respect to time. Then d by dt of omega t minus kx is equal to d by dt of some constant c. Okay, let us see with the constant. Then d by dt of omega t is omega, dt by dt is 1 minus k dx by dt is equal to dc by d constant by dt is, what is the d constant by dt? 0. So that what is the value? Omega minus k into dx by dt is equal to 0. That means omega is equal to k into dx by dt. Okay, then what is that? Dx by dt is equal to omega by k. Dx by dt is equal to omega. What is ds by dt? Rate of change of displacement of the wave. That is v. V wave. V wave is equal to dx by dt. Actually, I define delta x by delta t. Then for a small time, delta t tends to 0. This delta x by delta t will become dx by dt. Okay. Then this dx by dt is equal to omega by k. Are you clear this? So it is proved that velocity of the wave is equal to omega by k. V wave is equal to omega by k. Right? This is the proof I said. I said yesterday, I'll prove you tomorrow like that. Then what is omega? Omega is equal to, we have relation 2 pi n. 2 pi n, where n is the linear frequency. N is the linear frequency. Omega is the angular frequency. Omega is the angular frequency. Okay. K value, angular wave number, that is 2 pi by lambda. Angular wave number. Then what is V wave? V wave is equal to 2 pi n divided by 2 pi by lambda. 2 pi n divided by 2 pi by lambda. 2 pi cancel. N divided by 1 by lambda. This lambda will come up. Then n lambda. So V wave is equal to n lambda, where n is the frequency of the wave, lambda is the wavelength. Okay. Are you clear this? So two proofs. V is equal to omega by k or n lambda. Yes or no? Are you clear this? Velocity of the wave in terms of wavelength and frequency. This is velocity of the wave in terms of wavelength and frequency. Are you able to following? Say yes or no. Akshay Nandini, Munishwar Kumar. Okay, right, very good. Now, velocity of transverse wave. Velocity of transverse wave. Velocity of transverse wave. Okay. So, how to calculate velocity of transverse wave in a string or wire? Now, you can imagine the string is like this. So, one side is fixed. Then you can create a wave pulse here. That means movement up and down. Then it will create a wave pulse. So that the wave pulse is propagating like this. That is the transverse wave established in the string. Are you clear this? Transverse wave. Transverse wave pulse. Exactly you can say transverse wave pulse. You can say wave pulse also wave only. Combination of wave pulses is wave. Are you clear this? So let us say initially there is a tension T established in the string. Before giving a wave pulse, tension established in the string is, tension is T. Are you clear this? Now you can see at this wave pulse, this is formed like a curve, a pulse or curve. So the tension, how it is, the tension acting like this, tangent to this. Here also tangent to this T. Are you clear this? Tension acting along the tangent of the curve. Now this wave pulse you can like a circular arc. This wave pulse you can take like a circular arc. Okay, then the tension acting on this is like this, tangent to this here also tangent to this. Are you clear this? Both sides. Tangent. Okay. Now this wave pulse makes an angle. Suppose you can imagine this is a circle. At the center of the circle, this is like a circular arc I am taking. Okay, this is the center wave for the circular arc. Then you can draw a normal here. Let us say radius r. Then this is the tangent, and for the tangent tension will be T. Okay. So you can see here this is the circle. The circular arc tangent making certain angle theta. You can see here this is the circle. This tension tangent tension T making angle theta. This tangent line. Here also tangent line makes an angle theta if it is circle. This is theta. Are you clear this? So if it is theta, with respect to how we can take. So normally if you draw a circle like this, you can draw a normal. This is the tangent. Angle between tangent and normal is 90 degree. Are you clear this? Now this with respect to circle, the tangent makes an angle theta. Suppose this is a tangent line, this is the normal line. Angle between tangent line and normal line is 90 degree. Keep in mind. What is this theta? This angle between this curve and theta, tangent line. Now you can draw a normal again, one more line here. Okay. Now you can see this is the tangent line and this is the normal to this tangent. Okay. Now again, suppose you can imagine this is a horizontal line. This is the vertical line. Okay. Now again, angle between them is 90. Okay. Now, if it is theta, then this angle you can take. What is this angle? This is a vertical line. This is a radius vector. Then this theta is angle between this tangent and normal to this curve. Tangent and a normal to this curve. So you can imagine this is theta. This is also theta. Now you can resolve the components of this T tangent in terms of T cos theta and T sin theta. T cos theta and T sin theta. I'll show the diagram very clearly in the PDF so that you can understand very clearly. 1 minute. Original diagram I'll show you. Right, this can. Look at this diagram. This is somewhat a critical diagram. You can see here. Are you able to see the screen? This is like a curve for the center I have taken. This is the tension T, tangent to the curve, tension T. Then that tension T components I have taken. I did not taken as of now. First I have explained it's like a circle. So circle has radius r, tension T acting both sides. Okay. So tension T and this theta you can see here. With respect to horizontal, not normal. With respect to horizontal, this tangent T making an angle theta. Okay. Then it will be resolved into T cos theta and T sin theta. This is all T cos theta, T sin theta. Okay. Now the diagram we can draw once again. Right. Once again I draw that. So you can take like a curve. Like this, you can take a curve. Okay, for this a tension T like this, tangent to the curve. This is also tension T like this. Okay. Now you can take a horizontal line like this. This is the horizontal line. Here also horizontal line. This tension T with respect to horizontal makes an angle theta. This will become T cos theta. Here also it will make same angle theta. Then this will be T cos theta. Okay. Now with respect to this curve, there is a center C. If this is T cos theta, along this direction T sin theta. Okay. Then again along this direction here T sin theta. Clear this? Then with respect to center, let us define here center C. Then you can define like this, these points. Then you can take a normal. Then this is theta, this is theta. Are you clear now? This total angle at the center is 2 theta. Total angle at the center is 2 theta. Are you clear this? Because this is the tangent line, this is the normal. And this is the normal to circle. This is the radius. Okay. Then now this is T cos theta will balance. T cos theta will cancel each other. Then the resultant force acting towards the center is 2T sin theta. Resultant force acting towards the center is 2T sin theta. Are you clear this? 2T sin theta is the net force, F net. 2T sin theta is equal to, this is the necessary centripetal force for this transverse wave. Necessary centripetal force means, because it is forming a circular path na, so here Fc, necessary centripetal force. What is Fc value? mv square by r, where r is the radius, let us say. Okay, mv square by r. 2T sin theta is equal to mv square by r. Are you clear this step? So let L be the length of the wire, L be the length of the wire, m be the mass of the wire. Then this small elemental mass is here, small elemental mass dm, and this length is dl. Length is dl. So mass per unit length you can define. Let us say mu is equal to m by l, mass per unit length. This is called linear density. Linear density. Okay. Then for dm value, how to write? dm is equal to mu into dl. Mu into dl. Linear density into dl length. Are you clear? Then centripetal force acting on which mass? dm mass. Then Fc, what you can write? dm into v square by r. dm into v square by r. Are you clear this? Actual Fc means dm mass only. On the dm mass only it is acting. dm into v square by r. Okay. What about 2d sin theta? Total 2d sin theta. Then you can see here this arc. Total angle 2 theta. 2 theta is equal to arc angle. dl, arc length by radius. 2 theta is equal to dl by r. So from this F net you can say F net is equal to 2t sin theta. I can write for small angle sin theta approximately theta. So that will become 2t theta for small angles. So t into 2 theta. T into 2 theta. But t into 2 theta is how much? dl by r. dl by r. So this F net is t into dl by r. But that is equal to Fc. What is Fc? dm into v square by r. But dm is how much? Mu dl. Then Fc value mu dl into v square by r. Okay, you can take these are equation 1 and equation 2. So what is the necessary centripetal force? This is the tension force, that is F net. then 1 should be equal to 2. That is T into dl by r is equal to mu into dl into v square by r. What is this v? This v is the velocity or the speed of the transverse wave. V is the speed of the transverse wave. That only I am trying to calculate, speed of the transverse wave. Okay. So this dl cancel, r cancel. Then T is equal to mu into v square. Mu into v square. Then I can write v square is equal to T by mu. That implies v is equal to root of T by mu. V is equal to root of T by mu. What is this v is equal to T by mu? Velocity of the transverse wave or speed of the transverse wave. Speed of the transverse wave. Okay. So here what is T? Tension in the string. Tension. Tension in the string. What is mu? Mu is at linear density. Linear density of string or wire. Are you clear this? Linear density of string or wire. What is mu value? Mu is equal to mass per unit length, m by L. Mass per unit length. Mass per unit length. Are you clear this, all of you? The speed of the transverse wave v is equal to root T by mu, where T is the tension in the string and mu is the linear density of the string. Okay. Right. Akshay Nandani, terminal exam portions, I will tell you 1 minute. Are this clear, all of you? Okay. So this is very, very important relation. Speed of the transverse wave. Speed of the transverse wave v is equal to root T by mu, not T by m. Keep in mind, it is not m, it is mu. Mu is called linear density. Okay. Right. Now, based on this, we can calculate a frequency. Okay, frequency and time period also for a transverse wave. We know already v is equal to n lambda. Is equal to n lambda. Then frequency n is equal to frequency of the transverse wave n is equal to v by lambda. V by lambda. Okay, that is equal to 1 by lambda into root T by mu. Like this you can write. 1 by lambda into root T by mu. 1 minute, Suresh sir calling. Okay. Right. So I'll stop here up to this. Okay, last 3 minutes. The point is here. So up to this velocity of the transverse wave we have calculated. Based on these applications we need to discuss. That we can discuss tomorrow. That means on Monday. Monday portions I will tell you once again. Monday exam portions is oscillations. Oscillations. Oscillations full chapter. That is one thing. And second thing is the term exam portion. Term exam portions will be total syllabus. Can I write total syllabus? Actually, it is total syllabus. Okay, right. Okay, so I'll talk to once all the remaining teacher. If total syllabus given for all, then I will also give. Otherwise, let us say any exemption is there, we'll think about that. Actually, total syllabus you can talk about 15 chapters. 15 chapters, including waves. Okay, that is one point, but depends on the time and situation. Let us think about that. We'll finalize on Monday. I'll finalize. Okay, are you clear this point? On Monday I'll finalize the total syllabus. Okay, right. So And for weekend Monday exam, syllabus will be oscillations full oscillations full syllabus. Okay. So thank you, Ananda. I'll stop here. Thank you.